In this chapter, we shall formulate some other notion of compactness, some of which are weaker than our original notion of compactness, and one will be not comparable to the notion of compactness. In fact, these notions, the idea of these notions comes from the usual topology of real number. We know in case of real number the notion of sequentially compact and limit point compact, though these two notions are equivalent in the usual topology of R. So, what is limit point compact? We know that in the usual topology of R, every infinite bounded set has at least one limit point. We also know that in case of R, every sequence which is bounded has a convergent subsequence. Moreover, we know that these two notions are equivalent in the usual topology of R. Not only that, these two notions are equivalent with the notion of compactness in R. That means a subset of R is compact if and only if any bounded infinite set in that subset has a limit point. But in case of arbitrary topological spaces, there does not exist any notion of boundedness. So, we can't generalize these notions directly. In this chapter, we shall formulate these notions for arbitrary topological spaces, and we shall prove that for metric spaces all the notions are equivalent. Let us pass to slide presentation. In case of R with usual topology, we have mentioned that every subset, every infinite subset of R which is bounded has at least one limit point. But in case of arbitrary topological spaces, we have no notion of boundedness. So, let us propose the following definition. A topological space X is said to be limit point compact if every infinite subset of X has a limit point in X. So, immediately from this definition we can say that R is not limit point compact with usual topology, because in R Z is a subset of R which is infinite, but it has no limit point. But if we take a bounded subset of R with the subspace topology, then we can say that that bounded subset with the induced topology from R is limit point compact, because we already know that in case of R any bounded infinite subset has at least one limit point. In some ways, this property is much more natural and intuitive than that of compactness. In elementary analysis, we first encountered this property as Bolzano-Weierstrass property. This property is also called Fréchet compactness. So, first our target is to prove that In arbitrary topological space, compactness implies limit point compactness. One thing I want to remind the student that all the topological spaces I am considering in these lectures are considered as T1 unless otherwise stated. So, to prove that compactness implies limit point compactness, let us take a compact topological space. Then, given a subset A of X, we wish to prove that if A is infinite, then A has at least one limit point. If possible, A has no limit point. What happens then? Then for each A belongs to A, there exists a neighborhood, say UA, in X which meets A only at the point A. That means singleton set A is an isolated point. Now, A becomes an infinite set, each of whose points are isolated, which contradicts the compactness of A, because we have considered A as a closed subset and X being compact, A is compact. So, this proves that compactness implies limit point compactness. Now, for example, let Y be the two pointing set X, Y equipped with indiscrete topology. Recall that by indiscrete topology on a set, we means that the topology contains only empty set and the whole set. Now, consider the space X is equal to Z Cartesian product Y. Then X is limit point compact, as every non-empty subset of X has a limit point, but it is not compact because the covering of X by open sets V n is equal to singleton set n Cartesian product Y has no finite subcovering. Now, let us introduce two more notions of compactness. A space X is said to be sequentially compact if every sequence of points of X has a convergent subsequence. Again, we can say that R with usual topology is not sequentially compact, because the set of natural number, if we take it as a sequence, then it has no convergent subsequence. But if we take a bounded set in R with the induced topology from R, then that subspace should be sequentially compact, because in a bounded subset of R, any sequence must have a limit point, that means has a convergent subsequence. Another notion of compactness is countable compact. It says that a topological space X is said to be countably compact if every countable open cover has a finite subcover. Now, we wish to prove that following implication relations, that compactness or sequential compactness imply countable compactness imply limit point compactness. In general, there is no relation between compactness and sequential compactness. In fact, the first uncountable ordinal omega 1 is not compact, but it is sequential compact, and the uncountable product of the unit interval is compact, but it is not sequential compact. We shall come back to this discussion after Tychonoff product theorem again. So, now we will go to prove the implication relations. First, we like to mention that in a T1 space, limit point compactness implies countable compact. We shall come to the proof of this theorem later. Rather, let us first prove the following theorem. In a first countable space, countable compactness implies sequential compact. Let us take a sequence. Suppose some point of the space is such that every of its neighborhood contains a subsequence. Now, we use the first countability. If there is a countable basis say Bn at the point, then for every n, let us take a point of the sequence contained in B1, B2, Bn with an index greater than the previous one. This subsequence has to converge to the point. Now, take the closure of the sequence, it is closed and hence countably compact. If all points in the closure have a neighborhood that does not contain any subsequence, then there is no finite subcovering. Therefore, some point in the closure is such that every its neighborhood contains a subsequence. This completes the proof of this theorem. Next, we wish to prove that in a metric space, sequential compactness and limit point compactness are equivalent. To prove the theorem, let us consider a sequentially compact metric space. That means a metric space where every sequence has a convergent subsequence. Now, let us consider a subset capital A of X, which is infinite. We want to show that A has at least one limit point. Now, since A is infinite, we can extract an injective sequence xn from A. By our assumption of sequential compactness, this sequence have a subsequence which converges to some point x in capital X. Therefore, x is the limit point of the set A, being a limit of the subsequence of xn. Hence, we prove that sequential compactness imply limit point compactness. Next, we shall prove that limit point compactness implies sequential compactness. So, let us assume that in X every infinite subset has at least one limit point in X. Now, let X n be a sequence in capital X. We want to show that X n has a convergent subsequence. Now, if X n has only finitely many members, then at least one member of the sequence should be repeated infinitely many times. That means we have a constant subsequence of the given sequence which is convergent. So, we get the sequence X n has a convergent subsequence. Now, let X n has infinitely many members. That means without loss of generality we can take X n as an injective sequence. Then if we consider X n as a set, then this is an infinite set. Now, the space being limit point compact, this set must have at least one limit point, say X. Then we must have a sequence in the set X n such that n belongs to n which converges to the point X. This sequence becomes a convergent subsequence of our given sequence. That means our given sequence has a convergent subsequence. Therefore, we have been able to prove that limit point compactness implies sequential compactness. Therefore, we have proved that in metric spaces limit point compactness, countable compactness and sequential compactness are equivalent notations. Now, our final target is to prove that in a metric space sequential compact and compactness are equivalent notations. So, we have proved that all the notions sequential compactness, countable compactness and limit point compactness are equivalent. Here we have claimed that limit point compactness imply countable compactness. In fact, we can prove that in the following way. If possible, let UN be a countable open cover of a topological space X which is limit point compact. Now, let us consider the set X minus union of UI I is equal to 1 to n. If the above open cover has no finite subcover, then this set must be non-empty. So, we can choose some point x n from this set. In this way, we can construct a sequence in the space X, and by the limit point compactness this sequence must have a limit point which will provide us our required contradiction. So, we can also say that limit point compactness imply countable compactness. That means all the compactness, sequential compactness, countable compactness and limit point compactness are equivalent. Now, if we can prove that sequential compact and compact are equivalent in metric space, then it will be proved that all the notions of compactness are equivalent in metric spaces. To prove the fact that sequential compact and compactness, these two notions are equivalent in metric space, we have to introduce another notions called total boundedness. A metric space X is said to be totally bounded if for any epsilon greater than 0 there exist finitely many points x1, x2, xn in capital X such that the open balls Bxi of radius epsilon covers X. In generally, we call this a finite epsilon net. So, we can say in this way that a metric space is totally bounded if it has a finite epsilon net. Now, it can be proved that every sequentially compact metric space is totally bounded, which will help us to prove that compactness and sequential compactness are equivalent. One thing to note that total boundedness is much more stronger property than general boundedness in metric space. For example, we can observe that in the usual metric space R, the set Z, if considered with the subspace topology, then becomes a discrete metric space. Now, we know that in any infinite discrete metric space, every subset is bounded. In fact, every infinite discrete metric space is bounded, but that is not totally bounded. So, totally boundedness is much more stronger property than boundedness. Now, we wish to prove that every sequentially compact metric space is compact. Let X be sequentially compact metric space and let U alpha be an open cover. Let us recall the Lebesgue number lemma for compact metric space. It says that for any given open cover, there exists a number delta called Lebesgue number such that any subset of that metric space with diameter less than delta is contained in some member of that open cover. So, by the Lebesgue number lemma, this open cover also has some Lebesgue number, say delta. Let us put epsilon is equal to delta by 3, and by previous theorem we can find an epsilon net A is equal to A1, A2, An. That means there exist A1, A2, An such that the open balls centered at Ai with radius epsilon cover A. Now, for each k is equal to 1 to n, we have the diameter of the open ball B A K epsilon is less than 2 epsilon, which is equal to 2 into delta by 3, which is strictly less than delta. Therefore, by the definition of Lebesgue number, for each k we can find an u alpha I such that B A K epsilon is contained in u alpha I. Since every point of x belongs to one of the B A K epsilons, the class u alpha 1, u alpha 2 up to u alpha n is a finite subcover of u alpha such that alpha belongs to I. Therefore, X is compact. We have already proved that limit point compactness implies sequential compactness in metric space, and also we have proved that compactness implies limit point compactness. Therefore, in case of metric space we have that compactness implies sequential compactness. This completes the proof of the fact that all the notions compactness, sequential compactness, countable compactness, limit point compactness all are equivalent for metric spaces. So, in this module, generalizing some facts from elementary calculus, we have introduced some notions of compactness, and ultimately we have proved that in case of metric space all of the notions of compactness are equivalent. With this we end this module. Let us pass to another module.